Good evening, everyone. I hope all of you are doing well and are safe. Today, we have the third talk in our series of webinars, the Elementary Lecture Series, where we invite eminent chemists from around the world to introduce the current frontiers of research in chemistry to undergraduate and school students. Today, we have Professor Jyotishman Dasgupta from the Tata Institute of Fundamental Research, Mumbai, who will speak about solar energy conversion technologies, the scientific bottlenecks. We expect the talk to run for about 60 minutes or 70 minutes, but Professor Dasgupta has requested that questions be relayed to him during the talk. So what we will be doing this time is that you can just ask your questions in the Q&A box during the talk itself, and we will have pauses during the talk, and I shall relay your questions to him, and he shall answer them. So there will be probably no separate Q&A session at the end, and the entire thing is expected to last about 80 to 90 minutes, including the breaks in between. So feel free to just type your questions in the Q&A box as and when you have any questions. Professor Dasgupta completed his integrated MSc from IIT Kharagpur. Following this, he went to Princeton University and obtained his MS in the year 2002 and PhD in the year 2006. He was a postdoctoral fellow at the University of California, Berkeley from the year 2006 to 2010. He is currently an associate professor in the Department of Chemical Sciences at the Tata Institute of Fundamental Research, Mumbai. His research group is interested in deciphering chemical reaction mechanisms of photo-induced reactions, specifically at the interface of chemistry and biology, with an emphasis on the energy problem. So I will just move on to Professor Dasgupta so that he can begin his talk.
Okay, thank you, Anubhav. It was a pleasure. Actually, it's a pleasure joining in this evening for this talk, and I really would like to thank the entire team of Pravega and the Elementary Lecture Series organizers for this opportunity that they have given me to talk about a very relevant topic in the current age that we live in. Of course, we are in the midst of a pandemic, and this talk is online. There are sort of ways to think about this. The online platform is pretty advantageous for science communication. However, it's always nice to go back to a classroom and use a blackboard or presentation technologies that could enable, sort of pedagogical lectures to be correctly positioned. But whatever be the case, I think the topic that I chose today makes it very relevant that we can do this discussion online and reach out to as many people as possible. So solar energy conversion technologies really have a potential to transform the way we imagine sort of energy being delivered to us without the use of fossil fuels and other kinds of technologies which may not ever be renewable. So to sort of break down this part, I would like to suggest to all of you that you may be using your cell phones, your mobiles, and other kinds of battery handheld devices. All of you are sort of creating a lot of waste, and that in itself is a very important issue to think about, the environmental impact. But the government of India, as well as some of us in the research community, believe that renewable energy technologies could sort of bring sort of some semblance to the energy problem. If you look at what is going on in India for last several years, a decade now, almost 10 years back, India in its sort of modern technology in modern India, I would say, in 2010, we had a total energy production of 160,000 megawatt. Okay, and that's a lot of power. Okay, now if you look at the distribution of the energy coming in, there is a distribution of the sources from which you sort of get this energy. You have the major chunk is coming from coal. Okay, so you need to understand that coal has a finite lifetime on this planet. Of course, it can go on sustaining us for next 75 years or so. However, the environmental impact of burning coal is obvious to everyone. We increase CO2 in the atmosphere. Now, if you were to now think of that 160,000 megawatt, is it being distributed properly? Well, in terms of reaching out to the cities, it's done pretty well. Most of the power losses, of course, take away a fraction of this 160,000. Almost 30% is lost at the distribution of power. At the, considering the technologies we have in our country for distributing power through cables, so there is a loss of 30% transmission of power loss at the distribution sites. Okay, now if that were to be the case, we are anyway not doing enough to satisfy all parts of the country. Almost 18,500 villages. This is a approximate number that the government has given. Of course, it's more than that. And almost 50 million people are sort of devoid of power. They don't have power even today. Okay, so this number is almost 4 years back. I don't think this number has gone down significantly, but this is sort of the situation currently. Now, what the government had projected almost 5 years back was that it has to increase the generation of electrical energy to 800,000 megawatt, okay, which is sort of the 5 times the production that was in 2010. Now it's actually, the numbers have gone up to around 250. So this is slightly older numbers, but what we need is close to 800,000. That means you need to keep on sustaining yourself on existing sources that you have. Coal cannot increase. All the non-renewable sources cannot increase. You're going to finish them up. So you have to look for renewable sources, and you would not see much of the solar power here, but you can see hydroelectric and nuclear take a fair share. But in the rest, which is in yellow, you will have sort of other kinds of ways of generating power, and solar is one of them. Wind is another, of course. Now, the primary commercial energy, which is slightly different in context, it's about how much of fuel you are going to burn to generate energy. Like, for example, keep up with your transport cost, and that is also going to increase. So it's very clear that electricity generation and fuel technologies, creation of new fuel, technologies that can create new fuels, are going to be of importance in the next 10 years. Okay, and you need to figure out ways to do this. And one of the ways to think about it is solar power. Okay, and that's why the government had invested a lot of time and policy efforts to think of ways to get up to 100 gigawatt solar power by 2022, which is almost equal to the same which was the production at 2010, production coming from all these sources, but exclusively from solar would be 100 gigawatts. So that's a pretty ambitious plan. It's not going to happen till 2022, although efforts have been made. This is going to be pushed down the line, but hopefully technology can serve us better, and we can get to this number. So before we launch into whether we can do electricity generation from solar power, or you can synthesize new fuels for transport purposes, let's actually think about what is the solar energy conversion paradigm. So the paradigm goes as this, that you make solar cells or photovoltaic technologies, and when you make them, the idea is very old. You go back to almost 150 years back, when Henry Becquerel, a physicist, discovered the photovoltaic effect, which means that when photons are impinged on some material, one class of material, you can generate electricity. And the idea behind this is just making an interface between two kinds of semiconductors. One is a p-type semiconductor, the other is the n-type semiconductor. I'm sure you've heard about semiconductors, and I know all of you have done are in your bachelor's, but the idea of semiconductors, I'm sure, has been alluded to you previously through some physics textbooks as well as courses. So when two semiconductors are sandwiched in a p-n junction, okay, you have a chance of generating electricity because sunlight can excite the p-type material or the n-type material to generate electrons and holes. Okay, because these two materials have different electron affinities or Fermi energies, the generation of electrons and holes at the interface can be sort of driven by, of course, light, and then the separation of the electrons and holes can be driven by a circuit that completes and through this wire, and you can light up a bulb, for example. So the electrons and holes move in opposite directions, and they generate electrical power. Now we will go into the pathways of how this happens in more detail in the next few slides, but this is just a general idea that light can generate electricity at an interface of two different materials with different electron affinities. Okay. Now, one of the critical assumptions of this idea, the photovoltaic effect, is every photon will generate a single electron and hole pair. Okay, and the excitation of this light, when it generates an electron and hole pair, they are going to flow in the circuit in opposite directions, and they are going to again recombine, okay, and generate power. So you remember this, that you should remember this, that every photon leads to one single electron and hole pair. Now, how are these solar cells sort of evaluated? Whether you have made a good solar cell or a bad solar cell, that's important, because if I were to build a very ambitious plan of 100 gigawatt solar cell or solar power technologies, you should be able to evaluate devices that you fabricate in an industrial setting. So the idea is, of course, you're generating electricity. No better way to measure electricity than measuring currents. And what typically people do is, for evaluation of these solar cell devices, they use something called as a solar simulator. Okay, and this device essentially tells you whether your solar cell is efficient or not. And how does one measure efficiency? Well, if you look at this simple formula, which says eta equal, which is the efficiency number, is equal to JSC into VOC times FF divided by P in. I'll define these terms. The P in means the incident power that is input to the solar cell, which means the power that is coming from photons hitting the device. Okay, so this is the entire power that a sun can give in, okay, or your solar simulator having a lamp, the lamp can give out, right? So this is taken in the denominator, and in the numerator, you sort of go back and measure something called an IV curve, which all of you know, which shows the current versus voltage performance of a device. What that tells you is, when I am running the solar cell under illuminated condition, I will generate a voltage, okay, from the device. And when I'm measuring the voltage, I also measure the current, okay, simultaneously. So this green curve shows the IV characteristics of a solar cell. Now, the cell is said to be under open circuit condition, which is OC, open circuit, when you do not let any current pass through the circuit, okay? And you can just measure the voltage with a voltmeter. So this is the highest amount of voltage that can be generated without compensating for internal resistances of the device. So this is the VOC, which is the open circuit voltage, and the parameter that is on the y-axis, the curve when it hits the y-axis, which is the current axis, it's called the short circuit current. Okay, that is the maximum current that you can sort of get from the device at 0 voltage. Okay, so this in its sense tells you a characteristic of this device, and the best performance of the solar cell is actually at the MP, the maximum power point, where the voltage at the maximum power is VMP, which is nothing but the projection of this dot onto the x-axis, onto the x-axis, and the projection of this dot onto the y-axis is the current at the maximum power point. Okay, so when we sort of evaluate the performance, the power is given by I into V. So the theoretical maximum of the solar cell, the power that you can take out from the solar cell, is nothing but the product of VOC times ISC, which is given in the numerator. This JSC is nothing but ISC. J is just physics parlance for current, and that's it. But it could easily be written as ISC. Okay, so this V into I is the power, that is the maximum power that can be derived out of this device. However, you can see that the IV curve falls short of this maximum power. The area under the curve is nothing but the power generated by the device, and the theoretical maximum is a rectangular box, red dotted rectangular box, but the actual real power is integrated under the curve that is given by the green color. So this particular sort of mismatch between the real output of the device versus theoretical maximum, the ratio of this is nothing called the fill factor. The fill factor essentially is a fraction telling you how far is it from ideality. So this is usually given as a factor of 1 if if the green curve completely matched the dotted red line, but in a real device there are losses, and these losses actually the contact losses, and so these losses give way, and you have to sort of multiply the short circuit current with the open circuit voltage with this factor, and then divide it with the input power, and you can calculate a percentage, which is the solar cell efficiency. So this is a sort of a long drawn explanation, but it is important that you realize that this is going to be the most important number that people sort of associate with energy efficiency of a solar cell. Okay, so this is really going to be a point of discussion. We're going to look at this again and again, this simple expression, and try to derive significant science out of this. Okay. Now there is something else that bothers all of us. The sun does not produce equal intensity photons at all wavelength ranges. This is the solar spectrum. This is the integrated solar spectrum that has been plotted here. You can clearly see the solar spectrum ranges from almost 400. This is actually plotted from 400 nanometers to 300 nanometers to 2500 nanometers. You can clearly see that the intensity distribution is not the same. So your lamp in your solar simulator has to match this, because otherwise you are not going to measure the device efficiency properly. So all solar simulators try to match the solar spectrum, and that is the cost of the simulator. The simulator that you see here, they cost around a crore. A benchtop device costs around a crore, because all they do is make a light source which matches the sun. Okay, and what do we need typically? These numbers, one sun is a unit which matches 1,000 watt per meter square of photon fluence. That means that much power per unit area of photon fluence. Okay, so these simulators try to match one sun, and the one sun, if you were to just project it back on intensities, spectral intensities, you will see this is the spectrum of sun's colors of photons. Okay. Now your solar cell is pretty racist. It actually takes into account the color of photons and then utilizes these photons. Not every photon counts for the solar cell. Even if the sun gives you photons from 1100 nanometers up to 2500 nanometers, most of this is not absorbed by your solar cell and it goes to waste. You're losing this much of photons. So that means your efficiency is going to go down. Then the other problem is, even if you are utilizing most of the photons above a number, a threshold number, which is beyond the band gap of a material, you are not going to use most of this energy, simply because most of this energy is going to be lost due to thermalization. I'll come to this point slightly later, but just believe me that thermodynamics takes into account. That means when I'm exciting a material beyond its band gap, beyond the energy gap of its quantized states, you're going to lose some of this extra energy through thermalization in the material. And these thermalization accounts for 33% of losses. Not being absorbed, wastage of photons accounts for 19% in the solar spectrum. So you already have lost more than 50% of the solar spectrum without even thinking of the design. So this is going to be always there. So, almost 52% is lost. Now there will be some losses due to the way the solar cell is going to be put in practice. There will be reflection losses. There will be ways of, solar cell connection losses. There will be extraction losses of current, and that accounts for 15%. And what you're left with is available 33%. So most of your devices are going to at max work at the best efficiency of 33%. It's like the Carnot cycle, right? You're not going to use all the energy. And you're going to have a sink where you have to dump in some of the energies. And that sink accounts for almost 67% of the loss. So 33% is the maximum theoretical efficiency that you can reach with a solar cell, a single junction solar cell. So this actually, yes.
Yeah, we have a question. Prithvish is just asking, what is the full form of FF? Is it the ratio between the area under the green curve and the red dotted rectangle?
Yes. So this is the fill factor. It's called the fill factor, how much you fill the rectangle. Okay. So this is the ratio of the area under this green curve versus the area under the dotted line. Okay. Is that okay, Prithvish? Okay. So now the idea that you have a theoretical limit of solar energy conversion, it's very clear, and I think you cannot battle this out unless you have some clever ways, and we'll talk about some clever ways today. But this 33% is sort of the limit of each solar cell. Now, apart from this problem of the efficiency problem, there is also a cost associated with the material you choose. Currently, the solar technology that you use in your calculators, for example, is the silicon technology. It's a crystalline silicon solar cell. Okay, and these crystalline silicon solar cells, they are expensive simply because to make crystalline silicon, there is a lot of clean room technologies that need to be invested in. Of course, the entire Silicon Valley, which is in California, actually makes sort of chips, silicon chips, computer chips, very large, does a large scale integration of silicon wafers, and the computer is ready for you. However, silicon technology is pretty expensive in considering solar cell efficiency numbers. So it is important to keep in mind that current technology is actually rupees 30 kilowatt per hour. Now, when you pay your bills for electricity coming from coal and other kinds of hydroelectric and other kinds of power stations, you're not doing, it's an order of magnitude smaller. Okay, so you pay maybe a rupee per kilowatt hour. So if you were to think about this technology transcending your societal needs, it's going to be very expensive to use silicon. So you need to actually go by a factor, a factor of 5 or 6 down with the cost of a viable solar cell technology, and then that makes it clearly impossible to use silicon, and you have to think of other ways to do the same, hit the same problem. So there are two sort of big issues with solar energy conversion. Okay, and this is being enunciated in this slide. I'm going to remind all of you that I have mentioned that there is a theoretical limit, something called as the Shockley quasar limit. It was first actually talked about in 1961 by Shockley and Quasar, 2 authors, and this theoretical limit is named after them, is the Shockley quasar limit. This is 33% for a single junction solar cell. So this, you have to take into account this bottleneck. And the second problem is thinking of a way to come up with a cheap material. A cheap material means the material can be processed with minimal large-scale technology, expensive technology, and if possible can be, as chemists, we always think that processing a material in the lab through wet methods could lead to a very nice technology, and that is going to take you away from clean rooms, which silicon needs. Clean rooms are very sensitive to dust, but your own laboratory, chemistry laboratory, that's not that, the processes that we use, it's not very susceptible to a small amount of dust. Okay, so so this is really critical. These 2 points that you have to consider, these form the scientific bottlenecks that I had kept in the title. And in the red, I have mentioned ways to think about this problem. And the first challenge, of the first bottleneck, is the theoretical efficiency problem. If the 1 photon, 1 electron hole pair generation can be sorted out, that is, every photon leads to 1 single electron hole pair generation. If that is not the case, if you can make a material that can do double the electron hole pairs or triple the electron hole pairs, or maybe more than that with a 1 single photon excitation, you're going to go beyond the Shockley quasar limit. Okay, because you're going to generate sort of more electron hole pairs, and you're going to make use of all the photons that fall in the blue region. If you can somehow sort of absorb this and this high energy and generate sort of photons, electrons and holes with lower energy, and we'll come to this problem. The second idea, of course, with the bottleneck is regarding the material challenge, and that's a chemistry problem. Can you come up with materials that sort of get over the silicon fabrication issue, the crystalline silicon fabrication issue? So, of course, chemists have been looking at this question of going beyond silicon technology. They have sort of thought of cheap materials. Can you make molecular materials that can be synthesized easily in the lab and have large absorption cross sections, trap in light, and generate electricity? Okay, that's one part of the problem. There is other part of the problem. If you were to actually make these molecules, can you interface like a p-n junction? Right? I told that in a solar cell you have a p and n junction, 2 different semiconductor materials in a junction. Can you make a p-n junction? So if yes, can you make a reproducible junction and have solution processing of that? And then, of course, can you think of newer mechanisms of generation of charges or carriers? I'll come to the idea of something called a singlet fission, or multiple excitations being generated in the material, not just one electron hole pair. Exciton is nothing but an electron hole pair, but multiple such electron hole pairs. So, of course, for last 20-25 years, people have worked on this problem. This has been recognized, almost for 2 decades now. People have been making porphyrin kind of absorbers. You can clearly see this ring, the central ring. People have been making conjugated polymers. You can see these very nice pi conjugated materials with different kinds of absorption properties. Okay, you can see the tunability in these polymers. You can make a slightly yellow color polymer, a dark blue color polymer, and so on. So these are things that people have been doing. People have been so that they can capture the sun's entire spectrum. People have been making quantum dots. These are like very specific, again, inorganic materials which can be crystalline, and they have been able to tune their sizes and hence their absorption properties. And also a new kid on the block, almost a decade back, a phenomenal discovery was made that films which have one particular kind of solid state structure called the perovskite structure can be made use as a light absorber for solar cells. So these are some of these materials that you can play with. But let's look at what these materials have recently been doing. So people have been working in the lab and producing photovoltaic technology from these materials. You can get these idea of efficiency numbers from these materials by something called something called as the NREL chart, which is the National Renewable Energy Lab in the US. They generate these charts which sort of capture the latest research that's going on across the world, and they report numbers, okay? And you can clearly see these are efficiency numbers. None of them go beyond 33%. That's the first thing you should note. But you see there are different color curves, dots. I have put some of these indices here. You can see perovskite cells, dye-sensitized solar cells, quantum dot solar cells, organic tandem solar cells, and so on, organic cells. You can clearly see that these numbers hover around, for the organic materials, hover around 17 to 18%. Okay. However, for perovskite solar cells, they have gone up to 25% now. Okay, they're reaching the Shockley-Quasar limit. It's 25%. So, and if you see the dramatic improvement of solar cell technologies in the last 2 decades almost, you can see perovskite solar cells have caught on ever since its discovery in 2009. They have caught on pretty rapidly. The slope is pretty high. The organic photovoltaics, OPV, have grown, driven out slowly, but they are close to 18% now. This is slightly older paper from Gary Hodes, who had summarized in 2014 what were the numbers. They were close to 11 to 12% for the organics, while 16% for the perovskite version. But they have really now moved in the last 6 years. This has gone up to 18% and 25% respectively. So these two technologies, the hybrid inorganic organic perovskites and organic pi conjugate materials, have really shown promise to deliver a technology which is cheap. Okay, why is it cheap? Well, just a quick foray through this magic material of perovskites. You will be learning quite a bit if you just open Google and type perovskites. Perovskites are a solid state material that you can easily make in the lab through a solution deposition process. You can actually make this kind of a lattice ABX3, where A and B are two cations that need to be there, and X is an anion that compensates the charge. Now A can be an organic cation, or an inorganic cation. B can be again an organic or inorganic cation, but typically it's inorganic cations that are usually used in the for B class of cations or anions, B class of ions, and X is usually an anion which can form a good complex with the B inorganic. Okay, so these are octahedral in structures. In this case, I have shown something called PbI6 octahedron, where B is Pb, which is lead, and I minus is the anion. So PbI6 forms a octahedral, small octahedral, complex, and these octahedrons can be arranged with respect to the A. In this case, it's an organic cation. It's called the methylammonium cation for the structure that I have shown. And this particular entire structure is a structure which is called as a perovskite structure. Now, these perovskite structures can be very, very ordered and crystalline like this, as shown in the leftmost part of the image, where you can clearly see the B site inorganic and the A site cation. Okay, and they can also become two-dimensional if you were to isolate these octahedron from themselves and have organic spacers in between. Okay, so there is a very good control on making these solid state films all the way from 3D to 2D. In fact, because of this tunability, they can cover a whole range of light absorption within the visible range, or going all the way from 300 to 800. You can absorb, you can make a black perovskite material film and think of making a solar cell with it. In fact, very recently, a commercial foray by the Korean Research Institute, KRITC, generated large solar cell panels that can be large in the sense in the context of handheld solar cells. They can generate a solar cell panel with a 23% efficiency, and this was in 2017. Okay, 23% solar cell panel. Now, however, it's important to notice that this is actually, if this is so true, so good, why are we even bothering ourselves with other kinds of material? The problem is perovskite is very, very sensitive to humidity, moisture, as well as light. In fact, any solar cell that is made out of perovskite material degrades within few days to months. So if this technology does not have a lifetime, if you cannot make a solar panel that lives for years and years, like the silicon technology lives for 30 years, 40 years without any drop in efficiency. But with these kinds of material, the drop in efficiency is pretty rapid. In fact, you lose all your 23% and it becomes almost 5 to 6% within few days. And you will see decolorization of the material itself. So this is one of the big issues, and there's no question that there's a lot of research going on, a lot of money has been pumped to make this technology viable, and you might want to invite speakers who are working on this in a later session of these this elementary lecture series. But it's critical to note that this is very promising as a material. Okay. However, because of the degradation issues, other technologies which are, available to the chemist, like organic photovoltaics, are still sort of actively pursued. Organic photovoltaics have an advantage, of course. These are organic materials, and once you make these organic materials in the lab and make a device out of them, they are pretty stable. They're not as stable as silicon, but it has been figured out by long work from Michael Dretzel, who was proponent of organic based photovoltaic technologies, that you can at least get 10 to 15 years worth of lifetime of the panels, and this can really be a sustainable technology. In fact, in 2016, you can see Heliotech, the company called Heliotech produced a 13% organic photovoltaic device and sort of had panels, flexible panels of these devices. So with organics, of course, there comes flexibility, right? Organic materials are bendable, so you can actually make flexible displays, flexible panels out of these. Okay, so now where is the current science associated with it? Well, typically organic photovoltaic devices are made out of two principal materials, the P and an N junction, right? Remember, two semiconducting junctions, two semiconducting materials. So one is a polymer, which is an organic polymer, a conjugated polymer, something that looks like this, and a fullerene, which is again a conjugated molecule, fully conjugated molecule that acts as an acceptor. So when organic photovoltaics were first discovered, these were the two principal materials that were used. And now these technologies within India, a colleague and friend of mine, Dinesh Kabra, who makes these devices in the lab, can reach efficiencies up to 10%. Okay, you know, these are with fullerenes. If you were to go away from fullerenes, well, traditionally fullerenes were sort of used because of certain ease of fabrication. I will discuss that. But if you were to go away from fullerenes, due to some disadvantages that fullerenes actually move around, they're not very stable. They diffuse, continuously diffuse, and your connectivities of the P and N junction can change over time. So people have actually gone to non-fullerene based acceptors. Also, fullerenes have a cost problem. They're pretty expensive to make. So if you also make a small organic unit which can be synthesized, you know, you can also push the efficiency pretty high. In fact, a breakthrough has happened this year in February. A Chinese group reported 18.2% efficiency, lab efficiency of solar cells, and that was very clear. It was very clear that these efficiency numbers are pretty good. Okay. However, I have marked something pretty important here in the lower side, which is the number, which is the VOC, the open circuit voltage. Okay, now the VOC is a number which is important for measuring of the efficiency of the solar cell. It's almost like the batteries that you carry powering your you know, your devices, your mobiles. You know, you typically get lithium batteries. Of course, these batteries could be 1.5 volt. It's essentially that number if you were to compare the open circuit voltage. So if I were to make a 10% solar cell that can give off 0.77 volt, it's not pretty high, but this is a 10% device. Now, what we need to take into account is how much is the potential of the photons that are coming in. So in this case, where Dinesh made this device, Dinesh was using an organic polymer that could be excited, that had a band gap of 1.6 eV. Okay, that means the translatable energy being taken off with respect to the band gap is only 50%. You can see that 1.6 volt would have been the theoretical max that you could have generated out of this device, but you only got 0.77 volts, which is 50% of the 1.6 volt energy of the photons. It's clear that there is a lot of loss, and if I were to want to push this above 1 volt, it requires quite a bit of scientific understanding. And this is in 2019, by the way, guys. So this is still a huge gap. Now, even in the latest, in the best solar cell that you have, organic solar cell till date this year, with 18.2% or OPV efficiency, a band gap of 2.8 and 1.55 corresponding to this material, 2.8 and 1.55 EV, generated open circuit voltage of 0.86 volt. Not really much of an improvement. It's going towards 1 volt, but it's not yet there. So it's very clear. Yes.
Yeah, we have about 3 to 4 questions that are pending here. So if
Sure.
I could ask them.
Yes.
The first question is what is meant by lab efficiency and how does it differ from actual efficiency in the daily use?
That's right. And that's okay. So the idea of when you make a device in the lab, typically you make a 1 centimeter by 1 centimeter solar cell. Okay, it's really small. It's tiny. Okay, and you use the solar simulator, which I've shown here, which is not the doesn't have a lamp like the sun. Light is only coming in a focused area, and you put your 1 centimeter by 1 centimeter sample under this and you measure your efficiency. Now, this is very different, Anubhav, and people who are asking the question, from a lab sort of, from actual device setting. When you make such big panels, this is not a very big panel. Of course, it's a handheld panel, but panels like this, for example, in the first slide I had, this is a solar cell panel that is powering a tube light or a bulb. So this kind of panels, they are actually having a few inch by few inch solar wafers, and they are all connected in series, okay, to make one single panel like this. Now all are electrical connections. So you have hundreds of solar cells, small solar cells, which are connected in series. Okay, so when we actually mention percentages like this, 23% or even 18% in the lab setting, these are meant to be for very small device and very small applications. But if I were to make a very huge, large panel, these numbers, the percentage efficiency will go down. So in fact, if you were to think of covering the entire building of one of your ISC departments with a solar panel that could trap in light from the sun, these numbers of individual of the entire solar panel would drop down to at least less than 10%. Okay, so because of the connection issues, the losses, and also making large solar cell panels, making homogeneous films of these solar cells become very, very difficult. So there are these losses due to just scaling up of the length scale of each cell.
We have another question. Can organic substituted metalloids be used as more efficient materials over here?
Can organic substituted?
Metalloids.
Metalloids. Okay. See, the thing is, you can make any kind of device out of your choice of materials, but there are some limitations. Those limitations are related to the photochemistry, which I'm going to talk about next. So maybe we can discuss that after I go through the rest of the presentation with respect to understanding the basic photochemistry, what is really happening.
And about this organic polymers, we have other organic polymer and quantum dots sensitive to the oxygen in the air.
Right, that's right. So that's a very good point. Apart from perovskites, of course, organic materials are also sensitive to degradation by light and degradation by oxygen as well when they are working, when they're operational inside the solar cell. But the encapsulation of organic materials is much more easier and trivial than encapsulation of perovskite materials. In fact, quantum dots can also be encapsulated pretty well. So yes, it's a valid question, but there are techniques by which you can vacuum seal your device much better than in perovskite systems.
We have a few more questions relating to light harvesting systems and donors or acceptors. I think we should wait for those questions.
Okay. Okay. So one of the things that I really wanted to sort of bring in the aspect of what nature does. So this is all, of course, our efforts, right? 10%, 18%. These are all our efforts to make a solar cell. Now, of course, the solar technology has been, used by plants for a long time in a different way. Photosynthesis, which was discovered almost 4 billion years ago, has already invested a lot of time through evolution in optimizing how to do solar energy conversion within its own leaf, right? Plants have done that. So this is a slide just to tell you that photosynthesis is definitely a chemist's inspiration to think about this solar cell technologies. However, photosynthesis actually does fuel generation, not electricity generation. And that's one of the things that this slide wants to sort of put into context, that you know, we all know that light energy can be used to create fuels like glucose. However, photosynthesis typically produces only 1% of, you know, uses 1% of the energy from light to generate glucose. The 99% comes from other kinds of sources within the plant. The energy comes from ATP and other kinds of energy sources within the plant. So the amount of energy that actually gets utilized by a plant to make fuel like glucose and oxygen is only 1%. However, what photosynthesis does remarkably well is light harvesting. Okay, whatever photosynthesis, you know, these proteins receive in photosynthesis. This is photosystem 2. It's a reaction center which actually harvests light and generates electrons and holes for, of course, for doing this particular chemistry. But photosynthesis has a very good way of doing charge separation. You can clearly see that these reaction center complexes, which are nothing but proteins carrying chromophores, organic chromophores, pi conjugated chromophores, they can harvest light. They take in, they absorb light. This is P680. They absorb light at 680 nanometers, and then they can do very simple charge transfer reactions to generate, almost a unit quantum rate. So every photon generates an electron and hole in photosynthesis. None of the photons are wasted, but the utilization of the electrons finally to reduce CO2 really goes very, very wastefully, and hence you only ultimately, from 100% efficiency of charge generation, you only get 1% overall efficiency for fuel generation. So it's very, I want to make this very clear. Photosynthesis is a fantastic test bed for light harvesting and generation of electrons and holes, and essentially the reducing equivalents. Although the ultimate chemical reaction is very inefficient. Okay, but light harvesting is fantastic, and this becomes the basis for many people to think of new light harvesting materials, which is critical for a solar cell technology. So now going back to the photochemistry, the principal photochemistry of a solar cell. So of course, silicon, if you look at this as a material, it's a semiconductor, as I said. So now what are semiconductors? As you probably have known that semiconductors are materials which have a distinct conduction band and a valence band. These conduction and valence band are states where electrons can reside. These are just electrons, states that can take in electrons. So these are quantized states of your system of silicon, and you can clearly see that there is a band of states. So all these band of states in valence band, they're filled with electrons in a semiconductor, and then there is a band gap. There is a gap between the next set of states which are completely unfilled, and this is called the conduction band. Now, if you wear a metal, the band gap is going to be close to 0. If you wear an insulator, the band gap is going to be pretty high, close to 3 to 4 EVs. Okay. If you are a semiconductor, your band gap can be 1 to 1.5 EV, something in range for solar cell, photon absorption. So now, in case of semiconductors, of course, when you launch in light, you create an electron and hole pair. exactly what I meant when I have a single electron hole pair created. That means one electron is going to go from any part of the valence band to the conduction band. Now, this electron launching into the conduction band generates two charge carriers, one hole in the valence band and the other electron in the conduction band. And in a solar cell, you make use of both these charge carriers. The electron is transported out through a circuit separately than the hole. Okay, so in a PN junction, right, you have the p-type material which takes care of the holes and the n-type material which takes care of the electrons. Okay, so these initial excitations that are generated in silicon, they are called excitons, as by the definition, which means nothing but electron and hole pair. Okay, and these electron and hole pair are, since they have their charges associated with them, there is a very important Coulombic interaction that keeps them together, until and unless, of course, if these Coulombic interactions are overcome by room temperature energy, the thermal energy, then electrons can be free, holes can be free. You don't care about these excitons being existing, they become free charge carriers. So silicon actually is a material where you can generate free charge carriers. You don't have electrons and holes seeing each other coulombically. Okay, because hole is a positive charge, electron is a negative charge. They can feel each other coulombically. But if the Coulombic interaction is weak as compared to kT, which is thermal energy, which is close to 0.5 kcals per mole. If you remember, these numbers are pretty simple to think about. 0.5 kcals per mole is nothing but the energy barrier of a CC bond rotation. If you remember from your organic chemistry days, Gauss to staggered conformations when the CC bond rotates. These are close to 0.5 kcals per mole, and these thermal energies are there in the system at room temperature, which is 300 Kelvin. So under these conditions, the electrons and holes are free, and their binding energies are close to 0.2 kcals per mole. And room temperature is 0.5, so you can easily overcome the binding energy coming from the Coulombic interaction. And what is also interesting is the length scale of the initial excitons formed in silicon, which are weakly bound, are close to 10 to 20 nanometers. These are pretty delocalized. 10 to 20 nanometers means how many bonds? This is like 100 angstroms. So at least 100 bonds, CC bonds, they are delocalized across something like that. So you can clearly see that the length scale of these excitations are large, the binding energies are weak, and hence you can easily dissociate the electron and hole. You can actually make them as a free carrier. However, in molecular materials like pi conjugated materials, the photochemistry is slightly different. We all know the electrons and holes in molecules are very localized, right? So when you push an electron from a HOMO to the LUMO, the electron is still stuck on the same molecule. And molecules' length scale is not 100 angstrom typically. A molecule's length scales could be as small as few angstroms, right? So these electron holes are really close by. The excitation is localized to the molecule, and hence they are very strongly interacting, and the Coulombic interaction could be as large as 7 kcals per mole, which is 10 times larger than room temperature or thermal energies, and hence you cannot easily separate and make free charges out of. It's very obvious, right? When you put visible light photons on a molecule like benzene or a porphyrin or some molecule like that, you don't dissociate an electron coming out of it, right? Unless you go to UV, when you photo dissociate electrons with high energy. So it is very clear that you have bound electrons in these molecules, and when you have bound electrons, the electrons and holes are strongly interacting in the system, and you cannot create free charges that easily. But what you could do in molecular materials is something called as charge transfer, where you can bring two different molecular systems with different electron affinities, essentially the p-n junction in some sense, and you can sort of do an electron transfer from the original material which is excited, which is called the donor. In this case, the D is the donor, A is the acceptor, and you can do something called as a charge transfer. This charge transfer now makes the delocalization length longer. That means now the electron and hole, that means the radical cation and the radical anion, they are sort of far removed from each other. They are on two different molecules. Now, you can separate them even further by creating an array of donor and acceptors, and the electrons and holes can get separated with longer and longer distances, thereby reducing the exciton binding energies to 0.5 kcals per mole. In fact, you can use this idea of charge transfer and charge separation to create weak Coulombic binding energies, and hence go towards free charges. So in molecular materials, charge transfer step is key to free charges, and that's being depicted here in this cartoon representation. That when we think about charge generation and photochemistry in organic materials, as well as in metalloids, in other kinds of inorganic materials, what you really have to think about the exciton binding energies, or the electron hole Coulombic interaction energies. Okay, and in cases where you can do charge transfer, you can sort of get over the binding energies by moving electrons and holes from one molecule to another molecule, and so on and so forth. This is what photosynthesis does so beautifully, that every time that photon light shines in, there are chromophores. If you were to see in the figure that I have shown, these are all organic chromophores arranged nicely so that these charge transfer steps could move. These arrows showing individual electron transfer steps after excitation of P680. So it's very clear that you can generate a hole somewhere here, and at the end, electron somewhere on the other, the QB, it's a quinone site, and these are the chlorophyll sites. You can generate an electron here and a hole here, and you can separate it by the length scale of the membrane, which is 50 angstroms or 5 nanometers. Okay, so this clear illustration is done in this cartoon, that as you push the electron and hole further and further from each other, it becomes easier to free up charges. And either you can do electricity generation by putting these kinds of frameworks, molecular frameworks, on an electrode, or you could do catalysis. You can actually trap these individual charges and do redox catalysis, for example, at two different sites. One site for oxidative chemistry, another site for reductive chemistry. Electrons are here, so you can do CO2 reduction. Protons are here, so you can do water oxidation or something like that, which photosynthesis does so well, right? So this is the principal idea, and the goal in photovoltaic devices is to extract charges and electrodes, and in photocatalysis is to store charges and do multi-electron reactions at sites. Okay, now, so what do we do at TIFR? So, well, we sort of think about the initial steps till charge separation. Okay, we try to optimize charge transfer steps in different kinds of organic materials, and once we optimize these charge transfer steps, we can actually use them as photovoltaic materials, or we can use them for catalysis. So these are two simple examples I'm just showing as part of the work that we do. But in this case, you can clearly see that the D and A are brought close to each other. In this case, a D and A brought close to each other through covalent bond connections. So this is a donor, and that's an acceptor in a single strand of a polymer. So this is a donor, acceptor, pi conjugated polymer. Okay, and these are the classes of materials that people use to make organic photovoltaics, simply because these are actually absorbing in the visible. And when you make these donor acceptor covalent architectures, covalently bound architectures, you have something which bridges them, and this is called an organic bridge. So this entire system sort of revolves around connection of a donor and an acceptor, such that photon excitation of the donor will lead to a charge transfer to the acceptor, and then across different polymer strands you can move the charges and do charge separation. So that's how you free up the charges. In this case, I've shown a catalytic unit where the donor and acceptor, in this case it's covalently linked, this is non-covalently linked. That means the interface is non-covalent, where you have a sort of a confinement, a cavity, a catalyst that has been taken as a cavity and a molecule being put in, and the molecule upon photoexcitation does an electron transfer to the cavity and generates a charge transfer state. And these in this case, we store charges in the cavity in some way and do catalysis, photocatalysis. So these are the ways to use charge transfer for photovoltaics or doing catalysis. And what we typically think about in our lab is, how do we actually construct these interfaces? What are the requirements for constructing an efficient donor-acceptor interface for solar cell application versus a photocatalytic application? So that becomes the principal goal for our lab. But if you were to look at it from a perspective of a solar cell device, actually you really, when I see a solar cell, we typically outside on a computer, on your calculators, it's just a black thing with some lines, you know. It's a device which you cannot see molecularly inside, but this is how it is represented inside. I've put a molecular cartoon of a solar cell, which is an organic photovoltaic solar cell, and this particular cartoon clearly shows how complex the architecture is. When light falls in, there's a glass, there is electrode, then there are some polymeric layers, and then there is the main material that generates free charges. Then there is a back contact, another electrode, and then there is encapsulation. So there are multiple interfaces and multiple different materials in them. And this is a schematic of something called as the bulk heterojunction solar cell, or the BHJ solar cell, first postulated by Richard Friend, Sir Richard Friend in Cambridge University in 1995. And then, of course, the photochemistry of this was developed by Alan Heeger, who himself won a Nobel Prize in 2000 for developing conjugated polymers as materials for these solar cell applications. So, this entire solar cell design is very simple. What you do is you take a conjugated polymer like this, it's a polythiophene in this case, and an acceptor like fullerene. You make a solution in which both of these materials are soluble, a good solvent, where both of these materials are soluble, and then you spin cast. You just spin cast this material on top of an electrode surface, ITO, and when you spin cast it, you generate a film, you evaporate the solvent, and you let the film settle, and the film actually becomes something like this. It's called a heterojunction, a bulk heterojunction. That means polymer strands are individually, actually they make individual phases amongst themselves, and they interface with fullerene phase. Okay, this red circle in this diagram is a fullerene. This circles, that balls that you see, they are this becomes a heterojunction of space separated, nanometric phase separated polymer in green and fullerene in red phases. Okay, and the idea is this is entirely mixed like this throughout the solar cell. In fact, they make these very interpenetrating junctions such that when you excite the polymer, the excitation or the exciton, the electron hole pair, as we have discussed, they can move amongst themselves till the interface where there is a charge transfer. And this charge transfer allows freeing up of the exciton and generation of free charges. So this is the idea of fundamental idea of the photochemistry of the bulk heterojunction solar cell. And all my discussions later on will be with regards to what would be the ideal choice of this material. This excitation has to come, diffuse out to the interface. So it should live enough so that it can diffuse out to this interface and do a charge transfer. And then this charge transfer step should not again recombine. These charges should not recombine. So how does these holes and electrons move out in the domain is the principal technological insight that we have to bring in from fundamental studies. So I will take some questions here, Anubhav, if there are any questions.
An anonymous question. What is the requirement of such stratified design of the BHJ solar cell?
Okay, so the requirement is simple. If I just had mixed two different layers of the material and made a composite like a PN junction, right? I would not have been able to sort of do this charge transfer simply because these excitations have finite lifetimes. Every molecule's excited state has a finite lifetime. And if you do not make these domains very small, almost at the length scale, few nanometers, these excitations cannot migrate to the interfaces and do charge transfer. And if there is no charge transfer, you're going to waste that photon's energy. So these have to be very elaborate. These have to you want to ensure that there is a charge transfer at an interface, and there are many more interfaces. The smaller the surface area of these, so smaller the size of the domains, larger the surface area of the interfaces. Okay, so this is one part of the issue. The other is, if I were to sort of have these again interpenetrating domains, they form these wire-like architectures, and these wires actually transport electrons and holes independently. Okay, so it almost becomes a circuit within this entire photoactive material. So there are circuits which are hole carrying circuits. There are circuits that are electron carrying circuits. So you can imagine that these are very thin wires, interpenetrating wires, which have interfaces which are these charge transfer interfaces, and the excitations can be easily sort of taken to these interfaces, and free charges can be generated. So that's one part of the design. Okay, Anubhav, is there any other question? Then I can move.
Yes, Sujit has asked, what properties makes a molecule a donor or an acceptor?
Redox potential. So absolutely a good question. So I'll come to this in here. The idea that you have a donor and acceptor in an interface, the electron can go only one way. That is, if the LUMO level of this, every donor and acceptor molecules have HOMOs and LUMOs. If the LUMO level of the donor is higher in energy than the LUMO of the acceptor, this will be a one-way electron transfer process. So Sujit, what we need to know is the redox potential of the donor and the acceptor. Okay, and that sets the thermodynamic benchmark for the direction for the electron transfer. Okay, any other question?
There's a question, is there a way to produce energy in a usable form from ATP, sorry. Hence, if we are able to conduct cyclic phosphorylation as in plants, can we collect a sizable amount of energy in the form of ATP itself?
Absolutely, absolutely. That's a fantastic question. In fact, whoever has put in the question seems to be a biologist. It's right. There is a lot of work being done where actual cells, biological materials can be used to generate energy. In fact, most of it is for fuel generation, not for electricity generation, because you can't take out electrons from a living cell. Okay, you can't you can, but the efficiencies are are going to be very poor. A cell will not inject an electron into an electrode. However, what you could do is you can make the bacterial cell storehouse for fuels, right? And so you can do cyclic phosphorylation and generate membrane potentials across the membrane, and that can be used to do, say, proton reduction. Okay, you can couple it to a proton reduction by using a catalytic interface, and you can generate hydrogen gas, for example. So yes, the answer is yes, you can do that, but they are far more complicated and challenging, simply because you have to keep those biological material living all the time. You have to give them a source for energy as well. Then only they can do the work for you. So you have to provide them the nutrition to go on. That will be this sort of, if you can couple photon, some sort of photon absorption to a cyclic event to generate proton motive forces across the membrane, you can use those proton motive forces to now do proton reduction if there is a catalytic interface available. Yes, it can be done. Okay, so now let's go back to the portion of organic photovoltaics. I had mentioned to you that it's very critical to arrange these interfaces. So let's look at the energy diagram that is seen here. Now, Anubhav, I think I'm running way short of time. I'm still pretty much early in my slides, so just tell me when it will be sort of, I would at least require 15 to 20 minutes more for sure. Okay.
I think 20 minutes more is fine.
Okay. So, so in some sense, it's important to appreciate that the efficiency issue in organic photovoltaic cell, the understanding of it should come from our understanding of the energy states in molecular perspective. Okay, so when I'm creating an excitation, what I'm doing is I'm going from a ground state of a molecule or a polymer or a system to its excited state, and this is a state which I designate as an exciton or an excitation in the molecule. Now, once these states are formed, if I have to free up charges, I have to go through something called as the CT states or the charge transfer states, which have to go again through a charge separation of electron and hole, and these charge separated states they will be accessed by the system. So it's important that we understand the energetics associated with these states. When I think of this excitation in these domains, these energetics become critical. When I have generated an excitation in this domain and I'm moving along this domain, transferring my excitation from one polymer to another polymer and reaching up to the interface, again, the state energies of the charge transfer state is going to be critical to access. So charge transfer states have to be downhill as compared to the original excitation states. And then charge separate states have to be further downhill, because every time you do a charge transfer or charge separation, you also stabilize those states by changes in the structure. And hence, these energy changes are nothing but energy required for changes in the structure and stabilizing those states. So if you were to see, there is a loss in the energy from the excitonic states to the charge separate states that is automatic. And this loss adds up to the loss in the open circuit voltage. Okay, so when I create these states in my system and I make the electron evolve through these states, the electron ultimately will land up on the electrode somewhere at much lower potential than what was the exciton's original photon energy. So this is close to a band gap of say 2 eV, and your open circuit voltage would be close to 1 eV. So that means half of it is just lost, because the kinds of states you need to access to reach the free charge criteria is very complex. and hence you can clearly see your efficiency suffers. If you have a lower VOC, your efficiency goes down, and hence you need to think of ways in which the CT states and the CS states can be energetically higher in energy, and you can inject an electron directly at a higher potential than what is typically done. So these are some of the challenges that you face when you think about the thermodynamics of charge generation in organic photovoltaics. Of course, as a chemist, you would like to study this in a context, and as a chemist, we all know we love to study reactions, and every reaction, this is nothing but a chemical reaction of electron transfer. Every reaction has its own reaction coordinate, and as a group, we focus on understanding reaction coordinates very much. So if we have to think of ways to circumvent this problem of generating higher and higher efficient solar cell modules, you need to take into account pathways by which energy is lost while doing charge transfer, while doing charge separation, while doing interfacial electron transfer to the electrode, as well as you need to think of clever ways to generate more excitations from a single photon. And if you could do that, for example, do we really care if from this excitation we can generate 2 excitations at half the energy, somewhere here, okay, at half the energy? And if I can annotate it here, maybe, or maybe not. Okay, so at half the energy, if we generate 2 excitations, then we can just take these excitations and inject it in the electrode without any loss. We can actually get more current. So if these 1 electron hole pair can generate 2 electron hole pairs at lower energy, half the energy, then you can actually work at the same open circuit voltage but with higher current, because you have 2 electron hole pairs, and hence that would be a way to battle out the Shockley quasar limit. So these are the 2 ideas that I would like to talk about. Now coming to the idea of what do I mean by generating multiple excitations, multiple electron hole pairs in a system. So there is a process called Singlet fission, which was discovered long back in the community, which said that 1 photon excitation of a molecule, although fundamentally generates 1 excitation in a system, but if we can couple 2 molecules in such a way that they can share the excitation energy, you can in fact create 2 excitations. So that means 1 photon can lead to 2 excitations on 2 different molecules. Initially, this molecule was unexcited. Only one of the molecules are excited. So when you excite one of them, if there is a way to collaborate and share energy, you would be able to generate a new excitation. So this is a process called singlet fission. What this means is one single molecule's higher energy singlet can be fissioned. That means can be splitted into 2 excitations, but these 2 will not be singlet anymore. They will become triplet excited states. Okay, so in terms of the parlance of excitons, this is 1 single singlet exciton, 1 single electron hole pair, and in terms of triplet, these are 2 different triplet excitons, which are, these 2 molecules are close by and they're sharing the energy. But if you were to look at it, these 2 are individual triplets on the molecules, but then they are coupled together electronically to generate a singlet state. So this is the idea of singlet fission, where you can generate 2 electron hole pairs in some sense. This is an electron hole pair. This is an electron hole pair. Now the electron hole pair in this case is a triplet spin selective. So that means you have the electron and the hole both having the same spin, and in this case also the electron and hole having the same spin, and that's being denoted here in the bottom panel. So when I initially have two molecules in the ground state, you excite, you create one single excited state, which is the singlet excited state. You have the electron and the other hole, essentially they are spin paired, and you have an S is equal to 0 state for the electron. The total spin of the electron is S is equal to 0 on the singlet state. But when you have the two triplets formed, these are individually S is equal to 1, S is equal to 1, but see, these two are coupled in such a way that overall all the electrons are spin coupled to give S is equal to 0 state. Okay, so this is an effective singlet state, but it's formed through two triplets coupling to each other, and it is sort of very similar in total spin count to the original system. So the process in which you can dissociate this particular singlet state into two triplets is called singlet fission. And if you could do that, if you could generate two triplets, at a later point of time, you can separate these triplets and generate free electron hole pairs independently. So this entire chemical reaction is written here. The singlet fission denotes that when I have brought two molecules together, one as an excited singlet state, one as a ground state, I can generate a coupled triplet-triplet pair, which is effectively a singlet, and then dissociate them as free triplets by moving the triplet-triplet, by moving the individual triplets farther and farther apart by some form of diffusion, triplet diffusion. Then you can generate these individual triplet states. Now, this form of a reaction accounts for one photon generating two different triplet excited states. In essence, if I fall back on this diagram, what it says is my singlet excited state could be here, but my triplet could be somewhere in the middle, and I can generate two of these triplets, and I can use both these triplets to generate electrons or holes on an electrode surface. So if you were to use these individual triplet excited states and push electrons in, that will increase the current density that you generate in a device, and hence your ISC, or the short circuit current, will increase, which would lead to increase in the efficiency of the solar cell device. Now, of course, the singlet fission pathways are pretty complicated. As you can see, it requires a concerted generation of triplet on two different molecules. So there must be some criteria. There should be a thermodynamic criteria and a criteria which ensures, a physical criteria that ensures that in fact this can be done. So the criteria are twofold. Of course, the singlet energy, it should follow energy conservation. Whatever energy is being dumped by the photon in the molecule to reach its resonance state, that energy has to be redistributed. You cannot gain energy from anywhere else. So hence, if you have to create two triplet excitons, the triplet energies should be half the singlet energies. Okay, so if this is 2 eV, the triplet energy should be 1 eV, and hence two 1 eV triplets can be formed. Or in a sense, you have already sort of made sure that your open circuit voltage is going to be close to 1 eV. Okay, but if you can harness these two triplets, you're going to get two electrons instead of one electron as the current. So you're going to increase the efficiency. Now, apart from the energy conservation, which is the first rule, energy requirement, there is another important consideration, which is the electronic coupling between the two molecules. And what this means is nothing but you should allow for this process to take place. That means the singlet, this electron should be transferred in some way to generate sort of these triplet states amongst themselves. And one of the ways that you can do this is through a spin exchange method, where you can go through the excited state and generate an S1 in one molecule and have the ground state configuration. You can do an electron transfer from this molecule to the unexcited molecule, and then you can do a hole transfer and put the electron here and the hole here. So this exchanges the spins in some sense, and both the electrons on this side now are triplet in configuration and triplet in configuration, but you have clearly seen that you have moved from this particular singlet arrangement to this different singlet arrangement with two triplets in the individual molecules. So there has to be a special coupling that allows for this process to take place. And that is the electronic coupling that should happen between the two molecules. It's being designated here quantum mechanically through a transition dipole integral. But it's not necessary for us to have this discussion now. But what it means is there has to be a particular interaction that can couple a triplet state to the original S1 S0 coupled state. And if you can do that through some sort of a packing, you can pack the molecules correctly in the right orientation, you can do singlet fission. And that's what is going to be demonstrated in some of the examples that I'm going to take. But first, let's see what are the kinds of molecules that satisfy the energy criteria. These are conjugated polymers, conjugated systems. It can be polymers or conjugated molecules. You can have carotenoids, which are very naturally existing molecules in photosynthetic machinery. These are lycopene molecule, for example. This is a very nice conjugated system. Then you can take small conjugated molecules like diketopyrrolopyrrole or molecules like pentacene. All of them have a formulaic basis. The singlet energies are double the triplet energies. Okay, and if this is the case, we can probably pack them and get to the idea. So now let's quickly go through how we are going to look at these processes. We are going to use spectroscopy, and I think I'm going to quickly skip this because the introduction was too long and we didn't get to the point where we could talk about this. But what I would like to state to all of you who are learning chemistry and physics in your bachelor's program, that the interaction of light with molecules is what is studied in spectroscopy. And when we talk about these singlet states, whether it's a ground singlet state or an excited singlet state, all that we care about is what happens when light energy is funneled into the molecule, what state it reaches to, what kind of states it can access once it is starting to relax from the excited states to the ground state, what kind of processes that happen. All of this is given in something called a Jablonski diagram, which tells you that vertical excitations are nothing but absorption, going back, vertical de-excitations can be fluorescence or phosphorescence. If it's coming from a triplet back to the ground state, it's a phosphorescence event. If it's coming from singlet back to the ground state, it's a fluorescence event. And the spectra of these systems tell you about nothing but the energy states. So emission is always Stokes shifted with respect to absorption, because emission happens from the lowest excited singlet state back to the ground state. And if you were to excite to any other higher vibrational level or excited state, there is a process of relaxation, after which only emission takes place. So this Stokes shift is nothing but the emission, is nothing but a relaxation process that leads to emission. So a spectral feature captures this information. All of this is of course great when you have a molecule in the ground state and you get information about just the first excited, the second excited, and coming back to the ground state. But what happens when you excite molecule and you want to follow the molecule in time and go through as it is traversing through different kinds of states. Then what you do is something called as not just a simple spectroscopy, but time resolved spectroscopy, where you can monitor different states of the system in time in such a way that each of these states will have their individual absorption events. That means this state, when I reach to, I will measure an absorption. This state, I'll measure an absorption. Or this state, I'll measure. So as the states are evolving, I can measure transient changes in the absorption. And that would lead to information about the energetics of the states, the dynamics of interconversion, and also tell us about mechanism of how these excited states are connected amongst themselves and how we can tune the time scales of these states. Okay, so time resolved probing or time resolved spectroscopy actually forms the framework to sort of understand reaction mechanisms. And one of the things that we typically do, since we all know that photon absorption events are femtosecond in nature, we typically look at color of states. We sort of excite the system, and for each state that the system accesses, we measure the absorption spectrum. That means the color of that state. And this we do by a tool called transient pump probe electronic spectroscopy. What we typically do is we push our system with a pulsed laser, which is femtosecond in time, and we access the excited state in a system. It could be a singlet, it could be a triplet. If it's going through singlet fission, it could be a triplet. Now, once it reaches whichever state it is in, you probe with another femtosecond pulse that allows for very short time probing and looking at the dynamics. So it's almost like sort of watching a reaction happen while you have an excitation pulse, like a gun which starts a race, right? And you get spectra at different time points. So you get spectra at when you sort of have the gun starting the measurement, and a stopwatch that is sort of telling when the measurement has to be done. So in this case, I have shown you that when we excite the system at, say, some time point, you can start probing the system with a probe immediately at the same time point, which accounts for t equal to 0, which means that we have started an event. And then when that event has started, we can probe the system multiple times at different time points, from say 0 femtoseconds to 100 femtoseconds to 1 picosecond, 15 picosecond, and so on. Every time we bring a probe and we measure where the system is. So this allows for us to sort of capture events about the system in a time oriented manner. So in this case, we have looked at color of a carotenoid molecule at 1 picosecond. This is an absorption spectrum at 1 picosecond. This is a 15 picosecond absorption spectrum of the carotenoid molecule. This is a 500 picosecond absorption spectrum. All of them are marked now. See, I have written S1, S star, T. These are singlet excited states. This is a triplet excited state. All have distinct color. And we can watch where the molecule is at any point of time using this method. Okay. So the pump probe method is essentially allows you to watch molecules in time. And so one of the critical things that you need to understand in this is we are measuring changes in absorption. So when the pump is off, okay, we pass the femtosecond probe through the sample and measure its direct absorption. So that is a regular absorption event. When the pump is on, we again measure the absorption through the probe, and we plot something called as a difference absorption spectrum, where the pump on spectrum is subtracted with the pump off spectrum to generate this critical feature. Okay, you can see there are three important features to note in the spectral spectroscopy of these. One is the ground state bleach, which means some molecules have been excited, some molecules have been bleached. And this will be a negative signal simply because once you put, say, 10 molecules in the excited state out of a pool of 100 molecules, you will always get only 90 molecules in the ground state after that. So those 90 molecules will have a smaller absorption than the original 100 molecules when no pump was passed through. So when you subtract those, there will be a negative signal exactly at the absorption feature of the molecule. And this will be exactly the 10 molecules. It will be exactly the amount of 10 molecules that were excited. So that's much is the amount of molecules excited, 10 molecules excited. And those 10 molecules will actually give you emission, stimulated emission, which is a feature of this system. And also it can give you excited state absorption features. That means those 10 molecules, once on the excited state, can either absorb or de-excite. So if it de-excites, it gives stimulated emission. If it absorbs, it gives excited state absorption feature. All of this can be recorded with femtosecond resolution in your spectrometer. And this gives information, temporal information, every time of the system, just like this, 1 picosecond, 15 picosecond, 500 picoseconds. So when we looked at these material, for example, in this case, lycopene nanoparticles, and I will stop after finishing this part. This entire sort of exercise was done to see if these conjugated materials can actually do singlet fission. Lycopene has a very favorable singlet energy states and triplet energy states. You can clearly see that the triplets are half the singlet energies. The T1 state in this case is 0.85 eV. The singlet is 1.76. In fact, there are 3 or 4 singlet states that are interesting. There is a S star state, there is an S2 state. So the triplets are favorable in this case. You can see that 0.85 is almost half the S1 energy. So in principle, your singlet fission criteria of energy conservation is satisfied by lycopene. But then you have to find out a way by which these molecules can be coupled to each other so that the electronic coupling is set up and spins can exchange, can go around across the molecules, as I had shown you, so that you can form a triplet state on the unexcited molecule. So Arup, who is a senior student in the group, looked into this problem by packing these nanoparticles in well-defined aggregates known as the H aggregates. And he could do this very nicely simply because there are methods to produce aggregates like this, where you can just take your monomer lycopene solution, and put them in the monomer lycopene solution in organic solvent, and put them in a solvent where it is completely a bad solvent for the organic molecule, and it aggregates, it packs in as simple nanoparticles, that in this case it's water. This is just an example of a rapid injection method. This is actually not Arup's molecule directly, but it's a very similar procedure in which Arup could generate from the monomer, which was yellow, a nanoparticle which was red in color. And you can clearly see a change in the color in these systems because the monomer is sort of free molecules, just the lycopene, single lycopene molecules. And when you sort of put them in a bad solvent, they aggregate, they tend to aggregate and hydrophobically collapse to form these nanoparticles. And these nanoparticles are now strongly interacting with themselves, and they have a very different absorption spectrum. The monomer absorbs in the visible between 450 to 600, but the aggregate absorbs in the UV at 353 nanometers, clearly shown by Arup in this picture. In fact, you can also do the imaging of these nanoparticles. These are 40 nanometer radius, so 80 nanometer hydrodynamic diameters of these systems. So these are quite large size nanoparticles. They have been packed in. They have the nanoparticles force these lipopenes to stay together, and they actually can they can sort of pack them into an H aggregate. Now, when these particles come together, there are some very interesting quantum effects. These particles can have very specific transitions, which are not allowed in generic way. The monomers can have a single ground state to excited state transition, but in packed aggregates where there are dimers in certain oriented fashion, in this case, and Arup had made an H aggregate where they are card-like in sort of face-to-face, are facing each other, these lycopene molecules, and not head-to-tail like in J aggregates. There are very specific absorption events, okay? And these absorption are higher in energy than the regular absorption in the monomer, okay? So these are H aggregates that are made, which means that the molecules are card-like packing in with respect to each other, and their excitation, the blue shift, that means the visible to the deep UV change can be explained by a simple quantum mechanical phenomena of exciton interaction, exciton interaction between the two monomers. Okay, the monomers are being packed in card-like fashion, whereas there could be alternate arrangements like head-to-tail arrangements in which you can generate red-shifted aggregates, which have lower in energy than the monomer transition. So now comes the interesting part, whether these systems do follow singlet fission. So Arup actually measured these spectra, these beautiful spectra that come out from these systems when excited at the transition at 353. So you have pumped, you've excited the system at 353 nanometers, and what you're looking at, all the spectral evolution traces after the excitation. You are traversing through absorption spectra at 100 femtoseconds to 2 nanoseconds very clearly on this plot. You can clearly see there are so many different states the molecule is accessing. The absorption spectra is completely different, from 100 femtoseconds to 2 nanoseconds. You can also see there are some negative features that appear, and if you remember, the negative features correspond to the bleach, the ground state bleach. And you can also see that these features, they spectrally move from the red side of the spectrum from 550 to 750 nanometers to the blue side. That means in this case, the initial excited state is almost black, colored is black, while at 2 nanosecond, the excited states probably look red. Okay, so the color has changed. That means I have actually created new states. Okay, now if you look at the monomer, it's completely different. See, the monomer does not show this black color to a red color transformation, but it shows some other state transformation which has some negative features and positive features, but nothing up to a nanosecond. So the monomer is definitely different than the H aggregate nanoparticle. It's very clearly different. The states are different. The states that we are accessing are different. And also something to notice, the monomer does not live for a long time. Within 30 picoseconds, all the excited states have relaxed back to the ground state, and you don't live long enough. However, the nanoparticle lives for at least nanoseconds, if not more. Okay, so what happens here is explained in this contour plot. The lycopene nanoparticles, okay, when they come together, it seems to us, and through other kinds of methods, we have deduced that the initial excited state, which is almost black in color, actually gives rise to an excited state which has a spectrum which is completely different, which is blue shifted. And we designate these states by the simple chemical reaction of a singlet fission. The initial excited state has an S star, which is excited singlet, and an S0 coupling. That means this is the initial state. Then this evolves to something where the spin exchange has taken place, called the TT pair state, which comes from the evidence comes from the fact that there is a ground state bleach rise. That means one of the molecules which was unexcited got excited at a later time because it became a triplet state. So this rise in the bleach, that means more molecules getting to the excited state. Bleach means how many molecules went up to the excited state. So this rise in the bleach, since there is a rise, you can clearly see in this data also, in the contour data, there is a rise in this negative signal. That means increase in the negative signal. That clearly talks about that new molecules are going to the excited state. And that can only happen if singlet fission were to take place. And two similar molecules with exactly the same state, the triplet state, has been created. Then once these triplet pair states have been created, they actually separate, they can be separated out. That means they are diffusing out and they can generate a free triplet. How does one confirm that? You can actually confirm that by separately creating triplets in the nanoparticles by another sensitizer, which scheme that shows that the triplets are being generated. What Arup did was Arup created in red spectrum a triplet, just the pure triplet of the nanoparticle directly, and compared it to the triplets generated through singlet fission, and they match perfectly well. That told that indeed free triplets were being generated in the nanoparticle and they lived up to 400 microseconds, close to 400 microseconds. So it is sort of obvious that these lycopene particles can do singlet fission, and using tools used in femtosecond spectroscopy, you can actually follow these triplets, these states, the absorption spectra of these states, the time ordering of these states, and you can gather information which tells you that which kind of packing should work. So for example, monomers, even at very high concentration, do not show these kinds of signatures that is seen in the nanoparticle, in one kind of nanoparticle. So what we sort of got to is that the packing of the nanoparticles in a very well-defined card-like geometry allowed for a specific coupling between the molecules that allowed the TT pair to be generated, or the pair of triplets to be generated. And then these pairs of triplets dissociated in the nanoparticle because they could freely diffuse out and form free triplets individually that can now be sort of interfaced with an electrode, and electrons can be injected to the electrode. So this is sort of the example that I will end at today's talk, that shows that the issues with understanding the photochemistry of a system becomes very important to address, and especially if you could, in principle, understand the thermodynamics of the states, that is the energetics of the states, you can think of ways to beat the Shockley quasar limits by doing these very clever ideas where energy redistribution of a singlet state to generate two triplet molecules can serve in solving the efficiency problem in solar energy conversion. Of course, to follow this, all of this, you require tools that could watch excited states and get reaction coordinate information and reaction mechanistic information. So this is essentially what we sort of concluded from this particular work, that H aggregates and very specific. In fact, Arup looked at films of lycopene. He could not get this very clear signature of these triplet pairs. He looked at monomer solutions and there were no evidences of these kinds of triplet pairs. But when he went to the specific arrangement of H aggregates, he could see singlet fission operating very clearly. Now, since we have discovered this morphology, the question would be how to interface these systems with electrodes. And I'm going to skip few slides and come to this particular slide, which shows that with a recent paper that came out in 2019, Mark Baldo's group had shown that even with a silicon solar cell, this is this layer, the solar cell layer, you can add a singlet fission layer and go beyond the 33% of Shockley-Quasar limit. You can operate the solar cell at 29%. This is a silicon solar cell, operates at pretty high efficiencies of 29%. Add this singlet fission layer on top of it with another interfacing with another material and push it beyond the 33% Shockley-Quasar limit. This improvement in the solar cell efficiencies clearly suggests that if you could design materials, in this case, it was not lycopene, they used a commercial tetrazine molecule, but we believe that with lycopene, these lifetimes of triplet states are very enhanced, and whatever enhancement of 29% to 35% was gained with tetrazine, you could push it a little bit further with these organic nanoparticles, which have long-lived triplets, enough to do charge injection onto another part of the solar cell and get more and more current out of this device. So what this does is, if you can remember the solar spectrum, what this does is it takes in all the high energy singlet states that exist in your system that can be trapped by your singlet fission layer and dump it to the lower energy side. So that means your triplets are lower in energy, of course, but what it is doing is it's making sure that I can generate current from the high energy photons without wasting it to thermalization. If it was just the solar cell, all these photons will be beyond the band gap of this solar cell and you will lose in thermalization. But because you've added the singlet fission layer, there is another layer that absorbs these photons and goes back to the solar cell and adds current to it. So this is something that singlet fission promises as a technology to increase the efficiency of the solar cells. There are other ways to think about increasing the efficiency. I have told about the losses in the relaxation pathways. We have also looked at that. I'm not going to talk about this today anymore because we have sort of ran out of time. But what I wanted to convey to you is that energy and the temporal profile of these excited molecules, the energetics of the excited states and the temporal profile of these excited molecules are very important to understand if we sort of try to design newer materials. There was a question about metalloids or any inorganic materials that can be substituting organic molecules. Yes, you can, but you really need to understand the lifetime of the states. See, the monomers in lycopene did not live for long. There are multiple organic materials that do not have long-lived excited states. Okay, so it becomes important to understand these long-lived excited, to engineer long-lived excited states and also engineer the energy of the excited states. So this is something I would like to leave you with as a perspective. When we think about solar cells, we think about interfaces, and these interfaces have excitations moving across. Now, if you could do charge separation or movement of excitations in a extremely fast time scale, such that you have not lost your energy to thermalization pathways, that means loss in internal conversion, other kinds of pathways, you could, in principle, make a solar cell which again beats the Shockley-Quasar limit of thermalization. So this is something as a process called hot exciton dissociation, something that you can take home on. If people can think of materials where interfaces can be constructed in such a way that entire photon energy that was delivered was immediately used without any loss to thermalization at an interface, then you could, in principle, again beat the Shockley quasar limit. But again, you need to think about the system, how the system are packed with each other, what are the defects in the system, how crystalline the material is, can excited states diffuse as fast as hundreds of femtoseconds and come to the interface. All these are challenges that I guess people like all of you can think of. So I'll end by saying this, that whenever you see a solar cell, do not think about just a panel like this. Think about the complexity of the photochemistry inside a solar cell. And that's how you will motivate yourself to think about newer materials and changing and making a mark in this community. With that, I would like to thank all my students who have contributed to the work, especially Arup, who is sitting here in this picture. Of course, I missed out on many other aspects of organic polymer work that I thought I would present today, but just the time was too short. But I would like to thank all my group members for actively sticking with me, even if even if I do not get a chance to show everybody's work, but it makes all the more sense that you share your enthusiasm and your excitement for work with all these colleagues, because they actually come up with new ideas every day, and they are excited in the endeavor that our entire group is part of. So and also I would like to thank Anubhav, Nikita and Anvesha, and many others who are organizing this elementary lecture series, for giving me an opportunity to talk about at least a part of our work. And I want to wish Pravega, the festival that these undergraduates are running, all the best, and have various kinds of talks. They have various kinds of talks, not only in chemistry, but also in other science disciplines, and that you guys have success this year doing through the online method, online conferencing tools. I would like to thank my collaborators, of course, Professor Satish Patil from Indian Institute of Science, Bangalore. Most of the work that I showed, as part of the work that I showed was with Satish, although the lycopene work was completely in TIFR. But with the problem on Singlet fission, we have been working with Satish and Krishna Priya, a graduate student in the group, senior graduate student in the group, looking at also other systems, pentacene systems coupled covalently, which I could not show you today, that generates again Singlet fission. In this case, with lycopene, we of course have non-covalent interaction of packing, but Krishna Priya and Satish were making molecules where two chromophores were covalently coupled. And of course, Professor Ravi Venkatramani for help with computations wherever necessary, and Department of Chemical Sciences, TIFR. And that's where I end. Thank you, Anubhav. I ran over by quite a bit, but I can take few more questions.
Okay, so I think we have just one more question, and the rest of the questions the audience can mail to Professor Dasgupta. One last anonymous question is, what about the stability and robustness of the lycopene for making a device? Isn't it easily degraded?
Very good question. Absolutely true. Lycopene can sort of degrade under conditions of extreme photon fluence. However, I would like to state here that the nanoparticles that we make, they need to be sort of encapsulated in principle if we have to interface it. In this case, right now we are only preparing these nanoparticles for spectroscopy purposes, and they are in water. They remain stable for if you keep it under at normal temperatures, they will remain stable for a week or so, or up to 2 weeks. But the point here is that you need to sort of have a stabilizing encapsulation to make sure that these nanoparticles are stable for a long time in a device. We have not tried out, Anubhav, the device making with this, but the goal would be to have a very similar interface as shown here, where these nanoparticles could be interfaced to a photoactive material or a solar cell. Yeah, so that's basically it. I just want to also add that in case where these materials are degrading, people have come up with solutions which which encompass adding sort of stabilizers, not just the pure material but stabilizers, which can either sort of allow for slight changes in the packing of these materials, but also allow for this recombination pathways not to take place. So one of the important things that I did not mention is this TT pair state can also recombine to go back to the S1, S0 state. And that becomes an issue in some cases because you lose, again, the photon energies. You lose essentially the photon itself. Okay, yeah.
All right, I think that's it for the questions. I'll move on to Nikita to deliver the vote of thanks.
Oh, okay. I just wanted to, can I ask one thing?
Sure, I'll send you live.
How long was this total talk?
Till now it's 2 hours and 6
minutes. Okay, sorry about that. Okay, thanks. Yeah, Nikita.
That's perfectly fine, sir. First of all, we would like to thank Professor Jyotishman Dasgupta for accepting our invitation and taking time out of his day to give us this extremely interesting talk about the scientific bottlenecks in solar energy conversion technologies, as well as about the promising materials and solutions we have so far. And also thank you for telling us about the fascinating work being done in your lab. That's inspiring and giving us something to think about. And yeah, maybe even got us to read some more papers. I would probably read more papers. Yeah, we would like to thank the Dean of the UG program of IISc, Professor P.S. Anilkumar, for making this talk possible. We would like to thank Team Pravega for helping and supporting us in the organization of this talk. And lastly, we would like to thank all of you for attending this talk, and we hope you enjoyed it. If you did, Pravega is hosting a bunch of other talks as well, which you can check out at pravega.org. The next talk being in collaboration with LIGO India at tomorrow 11 a.m. by Professor Shaumak Rai Chaudhary, the director of IUCAA, who will be talking about black holes, gravitational waves, and LIGO India. And as for the elementary lecture series, we will be back next month on 10th October, Saturday 5 p.m. IST with the talk being given by Professor Shantanu Mukherjee of Organic Chemistry Department of the Indian Institute of Science. Till then, thank you and goodbye.
Thank you.